So then because of this kind of intuition and leading to a very famous called Lemke-Howson algorithm. This algorithm is a way to using graph to explore the solution space and and find the equilibrium. We will see how this works. And so let's give example here is player one, player two. They do this zero sum. They do this general sum game, and the player one has 3 actions, and player two has 2 actions. So each axis here is correspond to one of these players' pure strategy. For example, player one have 3 actions. So the pure strategy could be 1 0 0 0 0 1 0 1 0, right? So basically we create this kind of surface. So equally, player two, we got 2 actions. Therefore, we got 2 pure strategies, 0 1 and 1 0. So anything mixed strategy is something in between this line, along this line. And so this here is introduce additional notation and the important concept called labeling on the strategy. Okay, so we basically to label an enjoined strategy. Okay, an enjoined strategy. Sorry, or an enjoined mixed strategy, and we denote it. Say for each of these mixed strategy for one of the opponent, we can label them, and also for another agent, their mixed strategy, we also label them. Put them together, we create a list of these labels. We can create a list of the labels. Then, just for the sake of notation, we use a given player as I, this another player as minus I. Okay, so the definition of the labels is the following. So mixed strategy xi, let's say for one of these agents, let's say I. Okay, we label their action as follows. So for each of the players' I's action, for their action, let's say in this case, this I player, their action, we basically go through all this action. In this case, is J. Okay, if in this previous example, that's player one, we basically for player one we have 3 labels. Okay, for player two we have 2 labels. Okay, so this is basically the J is the index of the actions. Okay, with each of the player I's action A, I, J, that is not in the support of Xi. So we basically have this A, I, J written down. If that is not in the support of Xi. Okay, so in other words, that in this mixed strategy, I don't play that particular J action, and I will notate that in my list as A, I, J. Okay, just basically list the action that I not play. And also with each of these minus I action, A minus I, J, that is a best response. That is a best response by player minus I to Xi. So in other words, that if they are sort of played, then you would basically have this A minus IJ indicate that that is a best response by player I minus 1 to Xi. Okay, so that is basically say I would do that sort of labeling. And I will give you an example. It's a very sort of a confusing concept, and when I'm reading this, also I feel very confused. But if you're looking at the example, that will be much clearer later. So this labeling, in fact, this labeling is just to characterize that what we explained, the property of that is that if you figure out all these items, right? The items in the not support and also items, the actions that are not in the support and also the actions that have a higher probability, therefore is a maximum value they actually achieved in the Nash equilibrium. And then basically, then if all these items are identified like this, right, then they are in the stage of Nash equilibrium. So the labeling is really just for that. The labeling is useful because a pair of the strategy S1, S2 is in the Nash equilibrium if and only if it's completely labeled. So in other words, that I would basically find all these J, right, all these J's, all these actions, no matter it's I, minus I, they were not in the support, right, is therefore not played, or is the best response, or is a best response. So that's basically what this means. So just want a pair of the complete labeled each action Aij for agent I must either played, as I said, either played by player I with 0 probability, or A minus J be a best response by opponent player -1 to the mixed strategy of himself, or must be the best response by the opponent player -I to the mixed strategy of himself, player I. So that's basically so this is basically, as I said, is to mathematically describe this complementary condition that given in this constraint of this, right? Because in the select variable, I is 0 exactly when this random action is a best response to the mixed strategy. So that's basically the precise reason. So let's just looking at this. So before we start looking at this particular algorithm, for the convenience, they also act this fictitious point, the origin there, but although it didn't really play a role here. So we got 0, 0, 0 and 0, 0 for player 2, 0, 0, 0 for player. So player 2's strategy space is really triangle, right? We got this 0, 0, 1, 0, and 0, 1 equally. That player 1 got this 0, 0, 0, 1, 0, 0, 0, 1, 0, and 1, 1, 0. So let's say this, how we're gonna label this. And when we try to really go through all these possible mixed strategies in the space, we first need to label each of the points there, right? And then we basically see all these labeled, whether they are, we consider label all these actions. If we consider label all these actions, and then we got a Nash equilibrium. So just looking at this for player 2, because it's easy to look at it from player 2, because we're going to call a 2 actions. So player 2, we start from 0, 0 to 0, 1. So in this case, so 0, 1 is basically the pure strategy that I play action 1 at 0. So I play first action at 0. I play second action as a probability of 1. So, and then if you from 0, 0 to 0, 1 is, we would all label A to 1. Right, we all also labeled A to 1. It's because none of them assign any probability to play action A to 1. Right? Think about this, is that none of them would assign the probability, just really fulfill the definition of that. None of them assign any probability to play action A to 1. So this action A to 1 means that this action means that I will play action agent 2 gonna play action 1, right? It's not the case. But here you can think about this, is A to 2 is because I would play the None of them will pay, action 2. So similarly, so that's basically similarly you're going to label that. So action A1 is the best response by player 1 to any of the mixed strategy, represented by a line from here, 0, 1 to here. So look, just looking at the probabilities that what you could actually get from for player 2. So action A11 is the best response by player 1 to play any of the mixed strategy represented by line from here to here. You can think about this. So when this player 2 choosing strategy between 0, 1 and 1/3 and 2 out of 3, in this region, okay, and then you're looking at this expected reward for this action, expected reward for this action, expected reward for this action. You can find that this action A1, this one, expected payoff would be would be larger or equal to any of others, only until when you basically reach here, and therefore you can actually in this point there's no difference between this action, expected payoff of taking this action or expected payoff of taking that action 2. Just do the calculation, because this is sort of 6, right? If it's 0 and 1, the expected payoff is basically 6, because we have 100% time choosing second action here, right? 0%. So basically expected value is 6, but they are all smaller than that. But when you gradually remove some of the probability on the this action 1 for player 2, and this value become smaller and close to this, right? Only in this point, you can think about that. The expected value of taking player 1 taking action 1 and also taking action 2 to be the same. So in this case, that you label this whole line here as A11, but also you in this particular point you actually label both. So the point here, that particular point would label both A11, A12, because that's the response. That's the best response that you can actually get from this opponent. So think about this: is that you label your as a sort of each of the points mixed strategy there. You label the action that is not in the support of your Nash equilibrium, but also you also label the actions of opponent's action. They are best response to you. And then by doing that, hopefully we will gather all these actions where they would either in the support or best response to the opponent. I think that's the intuition behind it. So just looking at example. So the line from 1, 1 to 0, 1 is labeled with A21 because it's not in the support, isn't it? But similarly, we can do that for A22. Then this, however, in this line here, as I said before, here, A11 is basically best response by player 1 to any of the mixed strategy between this line, and therefore we label that. And in this particular point, this specific Nash equilibrium, we would able to sort of index 2 or label 2. Sorry, we would able to label 2 actions, and both are for agent 1 because they're not not in the support, right? They are not in the support, but rather we notate it as because they are able to notate that A11 and A12 are best response to to that particular mixed strategy. So doing this, and this Lomkosian algorithm is really just to search the pair of these labeled spaces, and so that whether all these actions for both players are fully sort of labeled, right? And then they are in the Nash equilibrium. So in this case, we basically have is the following. So we will start with this. Is that so in this the player one, as we're talking about the graph here as a G1, and then this player two, their graph is G2, and then this index for this label player one is basically triple labeled, whereas the this player two is because they have two actions, therefore you only have two labels. So these are the examples. And if these two are selected, suppose, right, this is a mixed strategy for player one, this is a mixed strategy for player two, and then find that they are complement to each other. Looking at this, whether they are complement to each other. So we got A11, okay, so player one's action one being labeled, player one's action two being labeled, and also player one's action three being labeled by a player two, because it's sort of a best response. And then this also player two's action one being labeled, and also player two's action two being labeled. So you can think about all these actions for player one, all these actions for player two, they're all being labeled, and therefore it is one of these Nash equilibria. So this one as well, you can actually verify and say that, this is for action three for player one, and this is for action one from player one, and this is action two for player one, and this is also for player twos, the two actions. Therefore, you can actually see these two pair are also in the Nash equilibrium. So let's look at how this works. So we will start with, let's say, it could be randomly. We'll start from 0, 0. And the first thing to do is to really sort of say, okay, to looking at these two pairs, whether they are, being, all these actions are being labeled. So just looking at this is that you got, in fact, you got this A22 being indexed twice. Okay, A22 be indexed twice. Therefore, we need to basically remove one of them. Okay, so basically what you do is basically go over the graph and see whether you would have a find a solution. If you move in here, you can find this. They still have A22, right? Therefore, you don't want this, but rather you want to go here, because then you would remove one of these A22s. Therefore, potentially can leading to a good solution. So basically, go to is what you're missing is think about this. What actually missing is the A12. So basically, you want to search for additional A12. So you go to next. You want to try to compare with these two, right? You can see what happens. So for next step is actually moving here, and then we basically, once you do this move, you can then start to move this guy as well. So you can do this as well, and to find out equally, so you can also do this next step until you actually find that, okay, I have very good sort of a match because I labeled all the actions. So that's the Lomkosian algorithm. Is in fact only few algorithms that would work to show general sum game. And so I think this is sort of a very open question in terms of how to find Nash equilibrium. And so today we are, really spent in fact quite a few hours. We just really found some how to calculate or find the Nash equilibrium, and we started with very simple, right, based on the character or receipt of this Nash equilibrium, looking at 2 agents, 2 actions. We were looking at the linear programming later on, find zero-sum games, and this Howson algorithm basically find this a sample Nash equilibrium in the general sum case. So these are the references that if you interesting.